Cuyahoga. So this is Async.io by example. How many people here are familiar with Async.io? You've written asynchronous code, and yeah, all right. The next one is how many people just like add awaits to things until it works, and then yeah, okay, yeah, that's okay. So good. This is a and not to out people, but all right. So these are all going to be in Jupyter Lab here. So this is honest to goodness code, and I'm running the latest and greatest 3.12.4. So if you're watching this, everything might be out of date, YouTube people. But so I think we should start with the fundamentals then, and we'll just get started here. So fundamentals. We'll start with the spam here. Spam is an asynchronous function. You can tell because there's an async out in front of the def. This is also known as a coroutine. So we'll run that, and in the documentation of Python, you see that lots of functions are documented as being coroutines, meaning that they're asynchronous. And if we call async.io is coroutine on our function spam here, false. It's not a coroutine according to async.io. So like right off the bat, if you're unfamiliar with this environment, you're liable to be confused because it is not a coroutine, it is a coroutine function. So that's like one thing you need to know if you're expecting this coroutine to be a coroutine. It's not a coroutine. So I'll just leave that there as a thing. Let's call spam here with 1. So what does that return? Anybody want to give a guess? Is it the string spam1? No, it's a coroutine. So like this is the thing that is a coroutine. So coroutine functions return coroutines. But I don't think it's like a wrong term to say that spam is a coroutine. If someone says, I'm going to write a coroutine, they're talking about a function. And as I said, the documentation says coroutine. But you just have to make that distinction that there's this context dependency that if you're not familiar with the environment, you don't know that it's there, and that can be confusing when you think, is coroutine will work, or something. So now what? We have a coroutine. What can you do with a coroutine? You can close it right away if you decide, I didn't actually want to do anything with the coroutine. So we'll close it. Note that it's close, not cancel. That'll be important later. And then if we try to close it again, that's fine. So let's create another one. We can't do anything with it now because it's closed. Just wanted to throw that out there. Spam, let's make another one, spam42, and await it. So awaiting is the other thing that we do with coroutines. That gives the coroutine to an event loop in the async.io world, and will execute. It schedules the coroutine to be run, and it executes it, and that is what gives us, that's what runs the actual function, that coroutine function that you need. There's this two-part system where the coroutine and the event loop have to work together to get the final answer that you're looking for. We can, see, this is the, we can't run it. So we already awaited S once, and you can't await it again because the coroutine has finished and there's nothing we can do anymore. Also, if we tried to, let's break so if we closed it and tried to await it, cannot, it's closed, so you get a runtime error there too. Of course, you don't need to specify a variable. You could just await spam 200. That's the typical thing you'd do. So awaiting, or rather giving the coroutine to the event loop in some manner, is like the function of coroutine. What else can you await? So technically, anything that implements the dunder await magic method, I wouldn't recommend ever using that, though. That's kind of a it's too magical. It's like if you really need to match an awaitable interface, that's what you use. But you'll note that def here isn't async. Your await isn't async because that would be a coroutine, and avoiding the coroutine. So it's a little bit funny. No one you work with will understand, even if you get it right, and it's not recommended. I would prefer, or I would suggest you do just make everything asynchronous methods in your class if you need to await something. If you're writing your own future kind of thing, your own coroutine, that's when you use it, but probably not a go-to. But the real answer here that I'm looking for is the future. So futures are the other thing in the ecosystem that you await. And this is Asyncio. I should have caveated this. This is all, from this point, the Asyncio is its own library that has, like it's in the standard library, but there are other asynchronous libraries like Trio and Curio that can run asynchronous code, but they won't be compatible with Asyncio. So creating an Asyncio future and passing it to other libraries, you're in incompatible environment at that point. But I'm just sticking with Asyncio, keeping it standard, keeping it simple. So futures. So we can create a future and set its results, and then if we await that future, we get that result. Great. And unlike coroutines, we can await it multiple times. I can keep running it. They also have other features like done. You can see if it was set. You can just directly get the result if it is done. We don't need to have an await if the future is done. And let's see here. Let's just run through some examples of, so we just created it. It's not ready. It's not done. If we tried to get the result, invalid state, like that's an exception. But if we set it later and then call done, it is done, and we can await it, and of course we can result to get our 2. Yep. So that's all. Like that's the interface of futures, is that we get a result out of it. It's storing it for the future. And you cancel them. You do not close them. So I had this problem where I was accepting some kind of awaitable thing, and sometimes if I didn't need it anymore, I would have to cancel it, or sometimes I would close it. And like, I don't think it's obvious that if you just passed in spam from before that you would need to close it, but if you had like wrapped it in a future, you would need to cancel it. So if we cancel it, it's already done at this point, so we got a false there, but if we just created one and canceled it, we get a true, as in you can detect if this thing was canceled by you or was canceled by something else in the environment. If we try to await a canceled future, we get a canceled error. And same with result. You can't set the result, and you can cancel it multiple times, and you'll get false because this wasn't canceled at this time. And again, I'm not saying, like, this is all just like, this is how these things work. We're not actually using them yet. We'll get to that if you're just like, what is, I'm just explaining the interface in case you're not familiar. So these are nice functions that the coroutines, you can like grab the value directly. You'd have to go into the interface of the properties of coroutines where you don't tread lightly. Right, so this coroutine S that we were looking at before, it doesn't have result. You can't check if it's done easily. So I would say if you're writing a function, you want the interface that futures provide. You don't want to worry if the coroutine was already awaited somewhere else in the code. So if you pass a future to 2 different functions, they can both await it and be safe. If you passed a coroutine to 2 different functions, one would work and the other one would say, this has already been awaited somewhere else, which is bad. So like, coroutines are the thing that are returned by the function. Like they're a necessary thing, but the interface you want is this other thing, if that's making sense. So if you want money and you want to be sure you have money, the awaitable type that you have should be a future and not a coroutine per se. It could be any awaitable, but we're not going to use my func there. That was just. So that interface of what happens, how do we get a coroutine and a future to be wrapped in, that is what a task is. In Asyncio parlance, that a task is a future, so we can run is subclass here. Task is a future that has the coroutine in it. So when the coroutine is done, it sets the result of the future to be the value of the coroutine. So that was a big like messy point for me understanding how these things interop, because it's just like you have tasks everywhere, and then futures are something else, but they're like they're more manual. But it's like that's true, but this is the relation, is that the task has the coroutine, and that's good. So let's see. They're not created directly. You don't create a task like from using the class itself like that. You always give it to an event loop, which schedules the future. Because the event loop needs to run the coroutine, the event loop will do that and give you the task, which is the future that gives you the value later. Is this clear? Is that like oh no, all right. I'm getting more. Anyway, let's do some examples then. So let's see. So co-row here is our coroutine, spam, right? Like the thing that you can await, but you can only await once. But if you give it to the async.io create task, which does the scheduling in the background, gives you this task, which is a future, you can await it multiple times and get spam, eggs, bacon. And you get all the future methods that I was talking about. You can check if it's ready with the done, check if it's canceled, you can cancel it, and that's all good. But this is all like a trivial example where we're still dealing with this like spam that just returns a single value. So we'll get into like why we're doing any of this in the first place in this example. So next example, a new spam. So we're replacing spam with this loop that we're going through n times with either spam or spamity, printing it, and then sleeping. So sleep is another coroutine that's provided by the standard library that will sleep, and when we await it, we have to, how do we think about this? So the coroutine that you're in is now waiting for this other one to be resolved. It won't be resolved until half a second later. Then it can continue on. So it's like waiting for this, well, there's no future involved here, but it's because we're not creating the task, but we're just waiting for this coroutine that's returned from sleep to be resolved. So let's just await this. It's an awaitable. It's a coroutine. So we'll do spam, 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 spammity, spam, spam, done. So we've waited for this spam to finish, which on each loop, we've waited half a second, so that's why they didn't run immediately. They're waiting half a second, half a second, half a second. Eventually, we're done. This returns none, and then we can print done. OK, is that clear that we can now chain these coroutines using the await, that we can always wait for something else to be finished? And again, this is all going back to the event loop. And that's like the standard coroutine one. There's no tasks at this point. But if we do the create task, done is executed, like print done is executed right away. So that's different than the await, because we've created this task, which is a future that will eventually get the value of the result of the coroutine, which is none because we're not returning anything. We could return whatever here. So if I can time this right, task done. Shoot. Task is done now, but if I do that, task is not done. So this is parallelism, kind of, right? Like this is concurrency is what they say, but the idea is that we have a background task at this point, that the event loop is running, and because I'm in the Jupyter environment, like that's running the event loop, so each cell is its own like coroutine, so I can do the await here, but we don't need to get into that. But, all right, what's unclear is that, so the coroutine I'm falling into the trap of like, oh, well, here's all the pieces. Can't you put it all together in 5 seconds as I explain it? But okay, I'll just move on, and hopefully the pieces come into place. So I wrote that kind of funny. If you thought, why did I write a while loop like that? It's, oh, we can just delete these, I think. So I can pass in a negative number. So now what happens? If I pass in a negative number, I will never equal n, because I is greater than n. So we just get spam, 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 spammity, spam, 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 spammity, spam. And if I try to stop it, I get, this is an infinite loop. What can I do? Like, how do I move on from this example? Anybody? Oh, is task done? Task is not done. Task will never be done. We can cancel it. So if we hit cancel, there we go. Yay! So that's this thing that's happening in the background in this task. That's great. And if I was implementing that with threads, there's no thread.cancel. That you need some kind of crazy mechanism where you're passing in a future, like a concurrent future, or some other mechanism of like, stop this when this is true, when that future is true, and then hope that the thread actually is checking it at the right time. That's all handled for you in the Asyncio environment by the event loop and the await. So when spam hits the await, it goes back to the event loop and will be canceled at that point. It raises a canceled error, and you can get out of infinite loops in that way. Or if something's taking too long, you can cancel it if you don't need whatever you were getting. Great. So creating tasks. As I said, you have create task from Asyncio create task immediately. You can also, if you get the event loop, you can call create a task on your event loop specifically. So if you passed around a particular event loop, you can create it there. You can also ensure future, which can take a coroutine or a future. The create tasks require coroutine. Like it'll error with a type error if you pass it a task or a future. Ensure future, you can, again, this is like the nicer interface where I don't know what I was given exactly, but I know I can make a future out of it using ensure future. So that's doing the type check for you to make sure that the thing you're using is the future. And then task groups, so we'll get to that. And as I said, await here, I call it a pause point. I don't want to like an await point because await is the await point, but there's two others that coroutines have, the async for and async with, which are the async versions of generators and context managers, where you'll pause your coroutine until that generator is ready with its next value. And then when it's ready, you'll resume. Otherwise, and then the other one is just it's two awaits, one at the beginning, the a enter, and one at the end, like a context manager. So you'll have two pause points with an async, which may, and whatever it does, but you just keep that in mind, that there's these pause points that allow other things to run. In between the pause points, in between the awaits and the async fors and the async withs, you're in total control, but we'll see that in a second. Okay, task group example. So task groups are great. They're Python 3.10, I think they were introduced, maybe 3.9. Doesn't matter. You're beyond that by now, surely, right? So let's make another spam here that's just going to loop n time, with a proper range loop rather than is I not equal to n. And we're just going to print spam spam x, that first parameter, and sleep some random amount. So task group also has the create task, which it will schedule it on the event loop. But because it's wrapped in this async with, at the end of that, remember that's another await point, it awaits every task that was created with it. So for x and abc, so we'll call spam here 3 times with abc. So now this print done doesn't happen right away because we're waiting in between the print and the async with. So we get some random, I'll run that again. Random waits, spams, they're all running simultaneously, kind of. But then we get the done at the end because we've awaited all of them implicitly by using the task group. So that's really good. If you're fetching a bunch of stuff and you want to wait for it all to be done, like that's the best way to do it. Also, if there's an error that's raised from any of them, it will cancel all the other tasks in the task group, so you don't have to, so you can group them logically, and I want to fetch all this stuff. If any of them fail, just cancel them all and tell me about it, because I don't want to be hammering my database so much. How can we await non-async code? We don't have, this might be too much. Here's some example. I think I want, how are we on time? Oh, we're at halfway. Yeah, let's jump to 9 minutes? Okay. Oh boy. Okay. So we're just going to move to the point of view of the event loop. Like I think this will help. So here's a script, really easy. It's running the async sleep and just returning, like foobar async sleep. Here's our Python environment. Here's our stack. It does some initialization. It loads the script. It calls main. It calls, main calls async run foo, and now the event loop takes over. So when the event loop takes over, the event loop inside of it, there's tasks and events. So like that's just the state of the event loop. In my little imaginary model, it's not actually implemented like this, but whatever. And we've given it the task foo at this point, or rather, we've given it a coroutine and it created a task for us. That, so that starts to run. It's its own stack there, prints foo, exclamation point. And then it calls async sleep. Then as I said before, because we're awaiting, sleep is a coroutine itself. So it's this like little task thing. And we now go back to the event loop saying, OK, I'm foo. I'm waiting for the sleep to finish. So sleep its own little coroutine. And the event loop then will load its next event, or its next task, which is sleep. Sleep somehow creates some kind of event, like a timer event. I'm going to sleep, and that just sits there. And now the event loop can run wherever. Shoot. All right. So now the tasks can run. I was thrown off by the camera. OK, so there's an event. There's no other task to run. The whole program's just waiting, and there's nothing else to do. Eventually, the event happens. Sleep is woken up. Sleep then returns to foo. Foo can run. It now prints bar over there, and then everything is cleaned up. So let's introduce some tasks. So instead of just awaiting two things, we're going to create two tasks, doing do stuff and do other stuff. And then we're awaiting both of those tasks because they're futures and they're awaitables. So we can do that. Let's see. So we'll just run the same stack. At this point, we're creating a task T1 and a task T2 inside of foo. Then foo can do whatever it is that it wants to do. Tasks 1 and 2 cannot run. They don't start. Like it's not like multi-threading where you're executing anything. Up until you hit a pause point, like what I call a pause point, that await, foo is just doing whatever it is. So if you think you're running parallel because you've created these tasks, they never got a chance to even start running until you hit this await. So now, hey, event loop, I'm foo, and I'm awaiting T2. So foo is now an inactive task. It has this dependency. When T2 is finished, it should tell foo to resume. Event loop will actually prioritize T2 because it's now the thing to do. So now we have another stack going inside of T2. It can do whatever it wants. T1 hasn't started. Foo can't go because it's awaiting something. Eventually, it starts to read from the network or something. There's another event that it creates. And so now it's inactive because it's waiting for this event to happen. Now, T1, like the event loop says, hey, I have another task to do. So now T1 can run because the do other stuff is inactive. So it just returns a value, so there's its little value there. Eventually, the network responds with some value to be read. It goes into T2. T2 is run. Foo can resume again. Now we're awaiting T1, but that's already done, so it just gets the value. It doesn't have to do any more context switching, and there's now it can print or do whatever. I don't know if there's a print. Yeah, there's the print stack, so it can now continue, and that's how all these coroutines run. In my little model of tasks and events, it's not actually implemented as that, but I think it's a really good mental model, and then everything cleans up. So the idea is that this is the concurrency part. You have one stack that's only ever executing everything. In between these pause points, you have total control over all of Python. The GIL doesn't matter because there's no other threads running. You can change lists and dicts and every global variables without worrying about unless you have other threads running, but don't do that. Your other tasks can't affect anything in between the event loops, or in between these, what I call pause points. And the parallelism, because there are things running in parallel. You're waiting for the user, you're waiting for the network. You've got some timers that are all clicking away. The rest of the universe is running in parallel. That's in the form of these events. So there's some kind of thing at the end of all of your futures that are waiting on real things happening. You've pushed all that, the complicated parallelism, into the rest of the universe, and all that's happening at the same time, but you're only ever responding to them one at a time whenever they're ready. That's the key point of the async IO environment, is it simplifies some code because you can reason about it easily. And I only have 2 minutes for the Pokemon, so that's too bad. So now for some real examples. I wanted to do, so I used a HTTP asynchronous library, HTTPX, which I'm not endorsed, I just happened to choose one. And it has an async client. And I'm using a Django application called PokeAPI, which just provides a bunch of Pokemon data in the form of REST endpoints. So let's create our client. Let's get our Pokemon 25. Anyone know what Pokemon that is? Who's that Pokemon? It's Pikachu. So here's a big thing of JSON. It's way too big. But luckily, Jupyter has this JSON viewer. So if you didn't know that, here's a fun fact. So here you go. It's Pikachu. He's got moves. He's got, I don't know. There's slam, and then you could go. It'd be nice if we had time to keep on investigating the Pikachu data model. But let's see here. We'd want to wrap this in a function to clean that up, so now we can just get it. But I don't like this function because we are creating the connection within the function. We want that to be dependency injected. So instead, let's call getByIndent with C as a parameter. And now we can inject the client. But we're using this async with because that's the interface. And now we grabbed Onyx. Let's get to something important. I'll just run stuff. Yeah, I was kind of afraid of that. There's Jigglypuff. So here's some Pokemon. All right, so here we're looping through some Pokemon. Then we're getting each of them by ident using that function that I made. And then we're 1 minute. Okay. So let's see. So how do we improve this code? What's wrong with this code? There's a for loop, and the await is within the for. So we do one await, or we're waiting for something. None of the other awaits can run because we're waiting for that task. So we need to use tasks here and not just straight awaits. So there's some more. So here we go. I have my task group. So anytime you see a for or a while loop with an await inside it, you're running these things synchronously. Oh, yeah, the client. So I wrote my own little hack around their async client to show the requests. So 4, 5, 6 are all done, not asynchronously. This is very synchronous because we have this await. So instead, if we have the task group where we're creating a task, and then at the end of the task group, at the end of this block, we're waiting for all of them simultaneously. It will run. There we go. They all ran simultaneously, but OK. And I'm out of time. But hey, look, it's async, and there we go. So thank you. Thank you. And there's